Exponential equations and logarithms are more applicable to everyday life than a lot of the other functions that we learn about. And that's because they can have so much to do with things like this problem, which is the depreciation of a car. So really anything losing value over time. Or things like a pandemic and exponential growth of a bacteria or of an infection, or many other things. It can be used for carbon dating to figure out how old fossils are. So we're just going to look at one little application problem today, but we will have other application problems to look at in the coming 2 sections left to go, particularly with regards to money. Exponentials and logarithms are pretty important to find interest and how long it would take to pay something off, or to save money for retirement, or whatever the case may be. All right, suppose a new car loses a fixed proportion of its value every year. Its value after t years is v of t, so the value as a function of time t equals the initial value times 1 minus the rate to the power of the number of years. So v sub 0 is its initial value, r is the proportion of yearly loss. If the car was bought initially for $25,000 and loses 20% of its value every year, after how many years will it only be worth $10,000? So we're trying to solve for t. We're trying to find time, right? How many years? All right, well, let's plug in what we know. We're trying to know when the value will be $10,000. So that goes in for v of t. The value of the car is 10,000 after a number of t years, which is what we're trying to solve for. V sub 0 is our initial value. And then our proportion of yearly loss is suggested to be 20%. So that would be subtracting 0.2. You always change rates to decimals before using them. And then, of course, we're trying to solve for t, so we don't know what t even is. That just goes right there. All right, we've seen other problems similar to this today where we have things to simplify before we actually use logarithms to solve. The first thing that I see that really needs done is we need this exponential to be by itself. So we need to divide by the coefficient of the exponential. That means I'm going to divide by the 25,000, not by the 10,000, because right now the 10,000 is just a constant, and it's still going to be a constant even if we divide it by 25,000. The important thing is that we need to get our exponential by itself. So in this case, yeah, we're going to end up with a fraction, but it's not that bad. Okay, so let's go ahead and reduce this fraction, 10,000 over 25,000. It's really easy to reduce out those zeros. And then 10/25ths, doesn't that just reduce by dividing both the top and the bottom by 5? So 10 divided by 5 would be 2, and 25 divided by 5 would be 5, so that's a ratio of 2/5. And then over here, I'm going to go ahead and do this math. 1 minus 0.2 is 0.8. So instead of thinking of it as losing 20% of its value every year, it's going to be worth 80% of its value every year. That's kind of what that 0.8 means instead of the 1 minus 0.2. Same idea. Loses 20% or keeps 80%. Okay, at this point we have an exponential on one side equal to a constant on the other side. Let's go ahead and use a logarithm or a natural logarithm. It doesn't matter, base 10, base e, you pick. I'm going to go ahead and use natural log. It really doesn't matter in this one because we don't have a 10 for a base, we don't have an e for a base. It's not going to make any difference which one we use. So the natural log of 2/5 is equal to the natural log of 0.8 to the t power. And then we can go ahead and use our power property and change that to t times the natural log of 0.8. Of course, equals our natural log of 2/5. If you'd rather be consistent with decimals or fractions, you could change your 0.8 to a 4/5, or change your 2/5 to a 0.4, or you could just leave one as a fraction and one as a decimal. It doesn't really matter. Okay, now in order to get t by itself, we're going to divide both sides by our natural log of 0.8. So I already have natural log of 0.4 on one side, and now I'm going to divide by the natural log of 0.8 on the other side. Now you might be tempted to try to simplify this somehow, because 0.4 and 0.8 look like we should be able to divide those and get 1/2 or something. These are logarithms. This is the natural log of 0.4 and the natural log of 0.8. That is not the same thing as 0.4 divided by 0.8. So the ratio for this overall problem is not 1/2. Don't cancel anything that's connected in with something else. Okay, so now all we have to do is plug this in a calculator. So I should have just gone ahead with my approximate. Type this in. Make sure if your calculator doesn't put the parentheses in there for you that you do that part. So natural log parenthesis 0.4 close parenthesis divide natural log parenthesis 0.8 close parenthesis. Again, it wouldn't matter if this is a natural log or a log base 10. It's still just about the ratio. So we should end up getting approximately 4.1 years. I encourage you to try that with whatever calculator you're using to make sure you get the same answer that I did. And that way you'll know that you're plugging them into the calculator correctly. I think that's one of the main causes of mistakes in some of these chapters, is just not plugging them into the calculator properly with enough parentheses or with the right order of operations for your calculator to calculate it properly. So, only 4 years for our $25,000 car to drop to a value of $10,000. That's the sad thing about cars, is that they do lose value quickly. And then they just kind of sit steady in value for a while until they become a classic, and then they can increase in value again. Interesting things that you can study the math behind other topics that you might be interested in, like old cars. All right, that's it for section 4.3.